So another little bit of insight. So I can't talk and type at the same time. So this one here means that TCP has set flow control on. So at some point in the history of this machine since it's been up, the flow control at TCP level has been enabled. So that means something is not keeping up. And there are isolated case stats like this, and it's I'm quite lucky. I don't actually cover a technology. I don't cover sort of TCP or storage or virtual memory. Many of my colleagues do, but I'm quite fortunate. Sort of maybe I don't know, hover around or grub around in the dirt, but I can go and ask and say, okay, what's this flow? How would I observe the TCP flow control being used? And they say, there's a case stat for that. And it's really one of the benefits of getting sort of access to people who fix a code. So that's quite sort of kind of a case stat that I hadn't picked up on. But again, if NFS performance or network performance over TCP is important to you, then this may give some insight that there is a problem, and you're kind of waving a white flag.
Is it a coincidence that it's reporting 5, the same number of retransmits?
I suspect not. But that would be an assumption. Conjecture. Wow, yes. Right, okay. There's not going to be a lot of storage stuff going on here, but user demo dtrace io_through.d. So this is one of the demonstration dtrace scripts. So it's just cp user demo dtrace io_through.d. Copy it to your current directory, and then type control vi control G, go down to the bottom. And there's a whole lot of clever stuff that they tried to do here. But what I found it really good is just to take the bit here where they're trying to calculate the idea of throughput per second, because that's kind of not for my purpose. I'm sure they were laudable when they tried to do it, is just to take this lot out. So you're just left with this elapse. So that's if you look at what the probes are, this is when we go into a storage-based I/O, and this is when we come out of a storage-based I/O. We basically take the timestamp minus this, so we end up with the elapsed time of that I/O. And this I found really helpful in blaming storage vendors. And sometimes that can be us. So, in this case, we're doing some NFS stuff. And forget, this is nanoseconds, so divide by lots. So that's kind of 2 milliseconds. And this is the distribution. And it's really good when you see IOs of kind of 100 milliseconds, second, 10 seconds. But this, if you have 1 or 2 in the 100 milliseconds, that's actually more important. So it's this distribution, because this is just going to be a single disk here. So I think that would be 1 second. No, so that's 100 milliseconds. So these are between 32 and 64 milliseconds. There's 4 of those, but that's just a single drive. So this is how long the IOs are taking to come back. And I found that's a very quick. It's on every machine that's run Solaris 10 or 11. Use demo dtrace and can give you a kind of distribution of the IO latency, which is really important for something like, let's say, an Oracle log writer ratio. And so just to kind of close things off, I was mentioning the SMTX column, spin mutex. These are trivial numbers. There's not much going on this that would be lock intensive, but this may give you an idea of what I was talking about if you've got that sort of a server-side NFS. That's VM2. So there's the task threads. What you will see is you can find a bit of ZFS on here. ZFS? Oh, come on. Well, let's imagine altogether that we may not be writing at this time. So basically you'd be looking here for things that have Z at the top, you have ZFS, and you'd be looking at these and looking at, you know, when they're serious numbers, not 500 nanoseconds, but where the hold times were significant. That may indicate that you should be putting the finger at ZFS or the DNLC cache or whatever. So one of the last thing I want to do is just really demonstrate, can't type, so when they developed VM2, they really did think about how are we going to debug this, and they put a bunch of debugging commands in for to look at a whole bunch of stuff. So hopefully you won't have any interest in there, but it is there. But what I just kind of want to show you is that the kernel keeps a log of some of the decisions, the predictions that VM2 makes. And so, for example, at the top we can say, oh well, we had a surplus 8K page, and then we reduced the cache list. So that would be in effect the VM2's cache list. And we wanted a 4 meg page. So this is in effect a log, and when we did it, so sort of 3 seconds ago, we needed to do some juicing and some state transition. And this is in terms of prediction of what it thinks the short for or oversubscription of certain different sizes of pages. This makes a big difference compared to how the sort of previous VM used to do it, which is basically you ask for a page, oh right, I better go and see if I can find one, or I can't find any, let's start doing some coalescing now. So the idea is that we do it before we need it, do the prediction. And this is just a way of dumping out the prediction. So we can see some coalescing of 8K tiles down here, and that for 8K the state transition will go from shortage into deficit, and then it will do some work to try and resolve that deficit for that colour, for that L group, and that size of page. Right. Questions? Concerns? And ultimately, it's all his fault. Because I wouldn't be standing here if it wasn't for him. I'd still probably be in a smallish university in Mid Wales. So if this was, you're disappointed in any way,
it's all my fault.
It's his fault.
Okay, well, thanks very much, Clive.
Okay.
Great talk.